Hartman here again with science, Cold War science, or astronomy. It's not really Cold War science. And so in the last video, we covered ancient astronomy and astronomy in ancient Greece, and then the Copernican revolution. And in this video, I'm only going to cover Kepler's laws of planetary motion. And then the next video, I will cover the insights of Galileo and Newton when it comes to gravity. So we actually start Kepler's laws of planetary motion talking about Tycho Brahe. Tycho Brahe, I believe is how you pronounce it. Born in 1546. He's a Danish aristocrat and also kind of an amateur astronomer. He develops that passion for astronomy as a young adult. And what he does for decades is that he makes daily observations of the positions of the sun, moon, stars, and planets. And what's really noteworthy about his observations is the preciseness of it without the use of a telescope, because telescopes had not yet been invented. So it's pretty miraculous that he's able to do what he did without a telescope. And in 1600, he would join Johannes Kepler in Prague, an interesting way to introduce Kepler. And then the next year he dies, and then Kepler would spend several years and then taking Brahe's data to fit a set of laws for planetary motion. And Johannes Kepler is a very important man. Let's see where he is. Right there. Here's Kepler. Right. So Kepler created 3 laws of planetary motion. The first one, that planetary orbits are elliptical with the sun at one focus. I actually meant to pull this up somewhere. Greeks, as we've talked about, they envisioned the planetary orbits as perfect circles, but Kepler showed that they're not circles; they're rather ellipses, which is a curved geometric figure. So instead of being perfectly circular, they are oval shaped. Let's see if I can find an example here. Yeah. Okay. So, okay. Yep. I just want the image, please. Thank you. All right. So here we have an example of an ellipse. Okay. So in an ellipse, we have some kind of key parts. We obviously have the ellipse itself. We have 2 foci, F1 and F2 here. They're the focus. Then we have a semi-major axis right here and a semi-minor axis. We're not going to focus on the semi-minor axis. We just want to focus on the semi-major and the location of the 2 foci. Okay. What an ellipse is that the sum of the distances from any point on the curve to 2 fixed points is a constant, right? So basically what that means, if we go back here, is that at any given point on this ellipsis, the distance to the 2 foci is constant, right? So right here, the distance to the 2 foci is constant. From here, the distance to the 2 foci is the same, right? Et cetera, for again any given point on the ellipsis, right? And these ellipses have, I believe that's how you spell it, have what's called eccentricity. And eccentricity is the distance between the foci divided by the length of the semi-major axis. So the eccentricity of a perfect circle is 0, which means that it's weird that it should be. I feel like it should be 1 possibly, but I guess it's 0. I haven't thought about the math of it. But as eccentricity increases from 0, the ellipse becomes less circular in shape and more elliptical, right? So I guess, if you had a foci, if you had a circle, right, the distance, I guess there's no foci, right? That's what that is. Yes, there's no foci, so that means the distance to the foci is 0, right? Which means 0 over the length of the semi-major axis doesn't matter because it's 0, right? So that's why that a perfect circle is 0. And so as the eccentricity increases from 0, that means that the ellipse becomes less circular, right? So almost basically like taking these points and almost just kind of stretching them out a little bit more, right? All right. So that is the first law of planetary motion. The planetary orbits are elliptical with the sun at one focus, right? And then an imaginary line, the second law, imaginary line connecting a planet to the sun sweeps out equal areas in equal times. planetary motion. So I think they did an okay job of explaining this, but I think there could be better. So let's see if I can find a good image to help explain this a little bit better. Let's see, open image. Yeah, okay. So basically, again, I think they did a pretty good job. The radius of a given point in time, right? So the amount it moves along the orbit, right? The area of the distance between that between the sun and those 2 points is going to that area is going to equal the area of any given other amount, right? So basically, what it's saying is that when the orbit is closer to the sun, right, the orbit will go faster because it has to sweep along a larger area in relation to when it's further away, because the areas of those triangles are equal, right? A1 equals A2, right, which means that then this part right here is going to be smaller than this part, right, because the kind of, I guess, the dimensions of it's almost like a triangle. It's not a triangle, right? But the dimensions of this kind of triangular shape here, right, are much larger than this, right? And so to kind of make up for that, we have to go much faster here. Okay, I hope that made sense. I don't know if I did a very good job explaining that one. But simply put, when a planet is closer to the sun, it travels faster. And then when it's further in orbit, further away on its orbit, it travels slower. The third law is it's an equation. The square of a planet's orbital period is proportional to the cube of its semi-major axis. And here we have the equation, P year, which is the orbital period squared, equals AAU, the length of the semi-major axis in astronomical units, which is AU, in astronomical units, the semi-major axis of one astronomical unit is the semi-major axis of Earth's orbits, right? So basically, the distance from the sun to Earth, right, is essentially one astronomical unit, or at least the axis of Earth's orbit. So it might not necessarily be from the sun; it might be from the center point, because again, the sun is one of the foci, right? The sun is not the center of the orbit, right? So basically, the orbital period is related to the length of the semi-major axis, and this kind of interesting little pattern here. And then down here you can see all the different lengths of the semi-major axis and the lengths of the orbital period, right? As you see here, right, the length of the semi-major axis for Mercury and Venus, because they are the inferior planets, is going to be smaller than 1, as is their orbital periods. This is the amount of years it takes, right, for them to orbit. And you can go all the way down here to see Neptune takes 163.7 years to orbit, and the length of its semi-major axis is 30.07 astronomical units, right? I don't think I did a very good job explaining this. Maybe I'll come back and do this another time. But Kepler's laws of planetary motion are also what are called empirical, which do not provide an explanation for why they are. It just says this is the relationship of this aspect of nature. I'm not going to tell you why. It's just this is the data, right? But the insight for explaining why the planets are like this comes with Galileo and Sir Isaac Newton, right? That does it for this video on Kepler's laws of planetary motion. I wanted to keep this one as its own video just because it's so important. It's also not necessarily super related to Galileo and Newton. I mean, it is, but Galileo and Newton are more related to each other than they are to this particular section, right? So I hope I did Kepler justice. I don't think I did. I should have probably touched up on this stuff a little bit more, or at least done a better explanation of it. But thank you guys so much for watching, and I will see you in the next